So far, we've heard the basics about hypothesis testing and p-values and so on. Now we want to try it out and see if we can compute with it. For a first example, let's remember that poll that Allison told us about, where they said that the current mayor of Toronto was supported by only 42% of the respondents in a poll. Now you might want to draw conclusions from that. You might want to say, for example, less than half of the people support the mayor. The question is, would that be a fair thing to conclude? Can we conclude from the results of that poll that indeed less than half of all the residents of the city actually support the mayor? Well, to consider that, let's start by remembering that the number of people surveyed was n equals 1,046, and the percentage of them which said yes, they support the mayor was equal to 42%. So that means the true support of the mayor, call it P, is unknown, but the estimated support of the mayor from this sample is equal to P hat, which is 42%, or 0.42. So now we want to test as a hypothesis whether the true probability P of people supporting the mayor is indeed less than 50%. So to set it up, we have to have the null hypothesis, H0, which would be that actually it's true that half the people support the mayor, versus the alternative hypothesis that actually less than half of the people support the mayor. And the question is whether we can reject that null hypothesis and say, yes, actually less than half of the people actually support the mayor. Well, how are we going to compute the p-value? We should start by remembering that in the theoretical world, assuming H0, the null hypothesis, then we can say that, well, p hat minus p divided by the square root of p times 1 minus p over n has approximately a standard normal distribution. That's what we learned before. So in this case, it means if we fill in the values that p hat minus p over the square root of 0.5 times 1 minus 0.5 divided by 1,046 should have approximately a standard normal distribution. From there, we can say, well, what we observed under the null hypothesis would be that p hat minus p was the 0.42 of the population that we observed supporting the mayor, minus the 0.5 of the population that we're assuming under H0 supported the mayor, which of course is equal to minus 0.08. So to compute a p-value, we want to compute the probability of observing a value that extreme or more extreme under the null hypothesis. We want to compute under the null hypothesis the probability that p hat minus p is less than or equal to minus 0.08. Well, with a little rewriting, we can say it's the probability that this quantity that we said has approximately a standard normal distribution is less than or equal to some other quantity just involving some numbers, which turns out to say what's the probability that something with a standard normal distribution is less than or equal to minus 5.17. Well, 5.17 is a pretty extreme value for the standard normal distribution, and indeed this probability is only about 1 in 9 million. So we can say, well, yeah, the p-value here is about 1 in 9 million, and that's very small. That's so small that we can say the probability that just by chance, if the mayor's true level of support was 50%, that a sample would only find 42% support is so small that we can reject the null hypothesis, and we can say that no, it's not true that the mayor's support is 50%, it's indeed true that it's less than 50%. For another example, suppose we said, yeah, we can really conclude a lot from this poll. Maybe we can conclude that the mayor's support is less than 44%, or 0.44. Well, we can set things up exactly as before. Now the null hypothesis would be that p is 0.44, and the alternative hypothesis would be that p is less than 0.44. Again, this is a one-sided test, and again, we start by saying under the theoretical world, if we take p hat minus p and divide by the square root of the appropriate quantity, then we get something which has approximately a standard normal distribution. But in this case, we observed p hat minus p under the null hypothesis to be minus 0.02. So that means that the p-value is the probability of observing such an extreme or more extreme value under the null hypothesis, which in this case works out to the probability, once we readjust things, that a standard normal distribution is less than or equal to minus 1.30. Now, that's actually not so unlikely. 1.30 is not such an extreme value, and this probability is about equal to 9.68%. That's not so small. So in this case, it depends on our level of significance, but we probably can't reject the null hypothesis. So we probably say, well, okay, we were sure the mayor's support is less than 50%, but we're not so sure it's less than 44%. For another example, let's go back to that case of flipping that beer cap and trying to figure out if the probability of getting the red side up was 50% or was some other value. Well, in this case, we could write that the true probability of red is p, which is unknown, and our observed estimate p hat in this case was, well, we got 576 red flips out of 1,000, which is, of course, 57.6% or 0.576. So now the question is, our null hypothesis will be that p is actually 0.5, and our alternative hypothesis will just be that p is any other value besides 0.5. So this is a two-sided test. We're not trying to figure out if it's strictly less or strictly more than 0.5, just if it's different than 0.5. So in this case, under the null hypothesis, we've observed that p hat minus p is 0.076. So the p-value now should be the probability of observing in absolute value, because it's a two-sided test, an observation which is equal to that extreme or more extreme under the null hypothesis. And we can use our same trick as before. We can rewrite things by dividing by that square root of p times 1 minus p over n, and we end up saying that it's the same as the probability that the absolute value of a normal is at least 4.81, which is, of course, twice the probability that a standard normal is less than or equal to minus 4.81, because it could be less than minus 4.81 or more than 4.81. And that works out to about 1 chance in 650,000. So again, it's extremely small. And again, we can reject the null hypothesis and say, when you flip that beer cap, it's not 50% chance of getting red. Even though the fraction was pretty close to 50%, it's far enough away and we had enough data that we can say no, p is not equal to 50%. So in this way, we're able to test hypotheses for proportions or probabilities by rewriting the equation and computing the p-value. In this way, we know when to reject the null hypothesis and when we can't reject the null hypothesis. This allows us to form sound statistical conclusions about probabilities and proportions.